Hello students, welcome back. In today's lecture, we'll be taking up yet another very important topic, which is the Z transform. We have been learning in the previous classes about different topics on the circuits and systems. We have studied the Laplace transform, and what we saw in the Laplace, that Laplace transform was used for continuous time. LTI systems. Whereas the Z transform will be for the discrete time signals. So let's start with the basic discussion on the Z transform. So given a system, let's say we are given a system, and system is represented by, let's say, T, where you get y of n. If you apply any input, let's say x of n, then we know that for a LTI system, and here the LTI system is a discrete time LTI system. So we have a discrete time LTI system represented by T. So whose response, that is y of n, can be written as equal to some transformation on this signal. Now let's prove that the input, whatever you apply the input, so we will be proving, you will be proving that y of n is equal to lambda times z power of n. This is we want to prove. Let me put this in a rectangle. This is what we need to prove. And to prove this, how do we start? Assuming that we have a discrete time LTI system represented by T with an input x of n, discrete time input, the output will also be discrete in nature, called as a y of n. So therefore, we can write y of n is equal to t of x of n, where x of n is equal to z power of n, where z is a complex variable. So therefore, I can write this as y of n is equal to a transformation on z power of n. This is my exactly signal. And you know what the transformation will be equal to. Further, you know that we are dealing with a discrete time linear time invariant system. We are discussing a linear and time invariant. So we'll see both the properties, time invariance and the linear. So let us apply the, with the system being time invariant. What is the meaning of time invariant? That if you shift the signal, the excitation by some time, here time is also a discrete time. So that means if you have signal now z power of n plus some, it is shifted by some units, let's say n0. So since it is time invariant, your output will also appear to be the same. So you have output n plus n of 0. Now, since we know that the system is linear as well, so therefore, since the system is linear as well, so we can write this as equal to z power of n dot z power of n0. And since the system is for a linear system, so if you scale this signal by z power of n, your output also gets scaled up. So therefore, you will write y of n plus n of 0 will be nothing but z power of n0, which is a constant term. You are shifting the discrete by some value. N0 is equal to 1, N0 is equal to 2, or some other value. So this is a constant. So I can write this as equal to z power of n. Now, at n is equal to 0, so this n will be 0. So you'll be left with only y of n0 will be equal to z of n0. And what is this? And this particular, let me highlight this. And this part is nothing but y of n. So I can write this part, which is nothing but y of n. So I can put this value as y of n. So let me write it here as y of n. And when n is equal to 0, for n is equal to 0, this term will be equal to 0. So this will become as a y of 0. I guess there should not be any doubt. So you had y of n, putting it here for n is equal to 0, you can write y of 0. Now, what do you see? Since this n0 is arbitrary and dummy, since n0 is arbitrary and dummy, so therefore I can put as a n0, therefore we can write n0 nothing but let me say this as n itself. So if you put n0 is equal to n in this equation, so what do you get as y of n is equal to z power of n into y of 0. And what is this y of 0? This y of 0 is nothing but this del. So therefore I can write down, y of n is equal to this. Again, let me take one more step. Y of 0 dot z power of n, which is nothing but lambda times of z power of n. So with this one, you are able to say what this output response yn for the signal z power of n will be. So the response yn is equal to y0 times z power of n, which is nothing but lambda times of z power of n. Well, this was an introductory to the Z transform, where your Z transform will be used to simplify the problems containing the discrete time signals, and hence the discrete time linear time invariant system, discrete time, but LTI, linear time invariant systems. We'll see more in the coming videos. Thank you for watching.